Welcome everyone to Solar Turbines webinar today, Centrifugal Gas Compressors Made Easy. As we can see, we're participating in a poll. Thank you for those who are answering this question on which type of compressors are you most familiar with. Reiner, it looks like we have quite a good audience that's already familiar with centrifugal compressors, which is great. For those who are registered today, I want to let you know you have been entered in a raffle to win a signed copy of this Introduction to Gas Turbine Theory, which Reiner Kurz actually co-authored. And for those who've registered and are with us, the winners of the signed book will be announced later today, so you should hear from us. So I am going to get started here by sharing my screen. Just a moment. Okay, great. Again, greetings everyone, and thank you for joining Solar Turbines for the first in a series of webinars by Dr. Reiner Kurz, the first titled Centrifugal Gas Compressors Made Easy. Today we'll explore compressor principles, design, as well as their control. So let's begin. First, welcome to you all from numerous backgrounds and time zones. We really appreciate you spending your time with us today, whether it's the morning or afternoon or evening. My name is Danielle Robles, and I'll be your moderator through this compressor series. And I've been with Solar for just a little over 14 years in a variety of roles, from engineering to project management, and today as a marketing analyst in our marketing and product strategy team. In addition, I co-lead this turbine strategy team, whose purpose is to identify business strategies based on market conditions and customer requirements around our solar turbomachinery products. Before we delve into the compressor material, I'll provide you with some housekeeping points for today's webinar and an overall introduction to solar turbines. So for housekeeping, good news is this webinar will be made available on our website at www.solarturbines.com, and we'll be using live polling, so thank you for those who successfully used that already. A link should have appeared on the right-hand side of your window in the chat window, or you can type the URL directly into a web browser, which is pollev.com/solarpoll. So throughout the presentation, we'll take time to pause for Q&A after each section of material presented by Reiner to take questions directly from the audience. So we certainly encourage you to type questions. This is great content, but we want it to be interactive with your questions as well. So the chat box should be on the right-hand side, and you can remain anonymous if you prefer, or if you'd like, please include your name and contact information. This is also good in the event that we cannot get to your question. We can certainly follow up with you later. For any issues during the webinar or concerns with connectivity, please contact us at webinars@solarturbines.com. And now a bit about Solar, as seen in this infographic. Solar Turbines is the world's largest manufacturer of industrial gas turbines in the 1 to 23 megawatt size range. We started manufacturing back in the 1960s and are now a subsidiary of Caterpillar since 1981. We've sold over 16,000 turbines, 6,500 compressors, and into over 100 countries worldwide. And one thing I want to point out as a key differentiator of Solar Turbines is our customer-focused, diverse global workforce of over 8,000 employees, many of whom are in your very own time and space, since we have 65 sales and service locations worldwide. Here is a snapshot of our Solar Turbines gas turbine family, ranging from the 1.2 Saturn engine to our 23.1 megawatt Titan 250. Additional information and details on any of our ratings can be found on our solarturbines.com website. And here is a summary of our gas compressor family. We have a lineup of pre-configured compressors for both oil and gas production, for high pressure ratio applications typically, and gas transmission with typically higher flow, lower pressure differential. And Solar currently produces more than 150 gas compressors and performs over 200 compressor overhaul and restages per year. And we definitely see significant growth in the upstream and midstream sectors of the oil and gas industry. And our compressors are optimized for these market segments. Here is our Solar's complete package lineup. Solar's gas compressors are developed to match Solar's line of gas turbines, forming our compressor set package, as you can see here in the upper left, which is also available as mechanical drive, of course. Solar's compressors have also been successfully applied in a number of electric motor-driven, EMD, applications as well, as seen here with our Spartan EMD compressor set. Finally, we have a generator set package seen here optimized for oil and gas in the center graphic. And many of these design features of these packages support the specific needs of field applications in oil and gas industry with an emphasis on rugged and reliable, yet flexible designs with state-of-the-art aerodynamic and rotor dynamic performance. And with that, it is my pleasure to introduce our presenter, Dr. Rainer Kurz. Rainer Kurz is the manager of our systems analysis at Solar Turbines in San Diego. His organization is responsible for predicting compressor and gas turbine performance, for conducting application studies, and for field performance testing. Dr. Kurz attended university in Germany, where he received his doctorate in 1991. He joined Solar Turbines in 1993 and has held his current position at Solar Turbines since 1995, a total of 27 incredible years. Thank you, Rainer. Dr. Kurz was elected as ASME Fellow in 2003, and he has authored numerous publications on turbomachinery-related topics, with an emphasis on compressor application, dynamic behavior, and gas turbine operation and degradation. Many of his publications were considered of archive quality and were accepted for publications in engineering journals. He has received several Best Paper and Best Tutorial awards at ASME Turbo Expo conferences and was the recipient of a 2013 ASME Industrial Gas Turbine Technology Award. He is a longtime member of GMC Organizing Committee and the GMRC Project Supervisory Committee, as well as the Turbo Symposium and Asia Turbo and Pump Symposium committees. Thank you, Rainer, for your commitment and your contributions to this industry and Solar Turbines over the last 27 years. And with that, we'll hand it over to Rainer to get us started in the content of our presentation. So Rainer, this will be, if you can share your screen and unmute, we can get into our presentation mode.
Okay, good morning, everybody, and welcome to our presentation on centrifugal compressors. I also would like to thank Danielle for her kind introduction, and I have to say it has been 27 years that were very interesting, but also were a lot of fun. I really I'm grateful for the opportunity to talk to you today about centrifugal compressors. And this is essentially somewhat of a foundational presentation because we plan to follow this up with a number of other presentations on similar topics. So when we talk about centrifugal compressors in this context, I want to introduce you to the major components. We want to talk a bit about the principles, how these compressors work and are controlled. I'll give you a quick overview on some thoughts about how they are sized. And we then will finish this presentation with looking into a number of different configurations for these machines. If I look at a cross-section of a centrifugal compressor, then we see in this slide first the aerodynamic component of the machine. So the gas would come into the machine through the inlet, go through a vane, would see the first impeller, then go through a diffuser, and then through a return vane into the next impeller. And then we repeat that several times, and after the last impeller, we capture the compressed gas in a discharge volute. The axial forces that are generated in this compression process are balanced by a balanced piston that you see here. So the purple part forms the rotating component of the compressor. The orange part are the aerodynamic components of the compressor that are stationary. On the mechanical side, the blue part is the part of the compressor that is the pressure containing part. So we have a center body with two end caps. So that is essentially the component that has to withstand the pressure difference between the gas that I'm compressing and the ambient. To prevent the gas from leaking along the compressor shaft, I have dry gas seals on either end. The axial thrust, the residual axial thrust, remember we had talked about the balance piston, is covered by a thrust bearing. And then we have two journal bearings that carry the compressor shaft. The probably most prominent component in a centrifugal compressor is the impeller. And the components of the impeller include the hub of the impeller, the vanes, so these are basically the blades, and we'll talk quite a bit about the function of these blades in a moment, and typically a shroud that essentially helps us to avoid leakage along the impeller. So depending on how much actual flow the machine sees, I may have high flow or lower flow impellers. And you see in this graph that the high flow impellers have a larger through flow area than the low flow impellers. And because we're compressing a compressible gas, we typically see, or we always see a higher actual flow at the inlet at the first impeller compared to, let's say, the last impeller in a compressor. These impellers can be made in a variety of different ways. We can cast them, and that is actually one of the major manufacturing methods that we use, and we use an investment casting method that allows us a very high repeatability and a very high surface quality on these impellers. But we also can mill impellers. So we essentially use a machine tool that essentially cuts the flow passages into a piece of steel, or we can make two-piece impellers where we brace the shroud on top of the vanes. There are older design where the impellers are welded from three pieces. So you have the backside, you have the vane, and you have the shroud that are all welded together. But that gives significant limitations on what you can do aerodynamically. And on really old blowers, you sometimes, instead of welding, see that the impeller is riveted. After the impeller, and I had mentioned that in my slide, comes the diffuser. And we will talk about the function of that diffuser a bit more. The idea is that in the diffuser, we convert velocity, flow velocity, into more pressure. And an elegant way is to simply have, like in this picture, two parallel walls. And we get the diffusion or the pressure increase essentially because the through flow area entering the diffuser is smaller than the through flow area leaving the diffuser. There are other types of diffusers, diffusers where you put essentially airfoils into this diffusion area, or actual flow channels. One of the reasons why we really like to use the vaneless parallel wall diffuser is because that's the diffuser type that gives us the widest possible operating range for the compressor. And these rotors can come in a large range of sizes. You just see here somewhat of a size comparison, but it's always a stack up of the impellers with balance pistons and with areas for the bearings and the dry gas seals. The rotor design and Solar uses a modular rotor design as opposed to a solid shaft design that's used in many other machines. Is a design where we stack the impellers and then we hold the assembly after introducing stub shafts on the suction and discharge side together by a tie bolt. And that allows us a very easy assembly, disassembly of these rotors without having to break heavy shrink fits. The design is API 617 compliant. You may remember on the first slide the purple and the orange part. And the purple and the orange part is what you see here, typically referred to as a bundle. And this bundle can be introduced into the casing or center body in one piece. So that makes it very elegant if you have to restage the compressor. You can pull out this module in one piece. This, by the way, also this picture gives you an idea on how big these compressors can be. I also mentioned that we have dry gas seals at the on the shaft to prevent gas from leaking across the shaft into the environment. And these dry gas seals, the main components are a stationary and a rotating disc, and you see these also on this slide. So the green and the blue disc, and the idea is as follows: when the compressor does not move, this spring here pushes the two discs together, and there's very little leakage across the discs. Now, once the compressor spins, you see here in the disc some very shallow grooves, but the leakage across these discs when the compressor spins creates a force that pushes the discs apart. So we are able to run these discs at very high speed with a very narrow gap, with very little leakage, but, and that's important, with no metal to metal contact. So there is no wear and tear on this type of seals. And these are in the oil and gas industry today, the type of seal that is used in practically all the machines. And as I had mentioned, we maintain this very small gap by balancing the closing force from the spring with the opening force from this gas leakage through the stationary and the rotating discs. So this gets us to the first break for questions and answers.
Fantastic. Thank you, Rainer, for the introduction and that first section. We do have about 5 minutes for some Q&A before we proceed. And we have a question in from a participant on the phone. Amir in Pakistan would like to know, and I know we didn't cover this quite in this section, but which is currently Solar's software for estimating compressor performance in the field? What software do we use?
This is actually an excellent question, and I will talk a little bit about software in a later section. But essentially, Solar has a software that is called TurboCell. But without trying to throw around names, the key piece of software that you use to evaluate compressor performance uses an equation of state, which is something I will explain later. And Solar uses as a standard the Redlich-Kwong equation of state, but we have the capability to also use a number of other equations of state depending on the exact situation.
Great. Okay, Rainer, that sounds good. I think once we get to that section, we can explore software control a little bit more. So thank you, Amir, for the question. Back on dry gas seals, Rainer, how long do dry gas seals typically last?
I recently was at a conference where they showed at a booth a dry gas seal that was taken out of a compressor after 23 years. All that had to be replaced were some O-rings that are used in these dry gas seals, essentially to prevent leakage on the stationary parts. So the dry gas seal as such has really no wear and tear. And you design a system around the dry gas seals that prevents or if you do this right and you don't get any dirt into the dry gas seals while they're running, there is really no specific limit on how long they last.
Well, that's great, Rainer. Yeah, 23 years, that's a very long life for a major component in a compressor. Thank you for that. Question on the modular design. I noticed, and we have a question here on why do we use a modular design when you mentioned other manufacturers use a solid shaft?
In the oil and gas industry, especially when you focus on upstream and midstream applications, you have large changes in the operating conditions that these machines see. And there will come the point where, in order to optimize your production, you may have to restage these machines. And having a modular rotor is a very elegant way of making these restages simple, effective, and actually also very economical.
I see. So it's a ease of maintenance type of approach. This kind of goes into another question, I think, then that we have here on, can you remove that bundle in one piece then? Is it ease of access and easy to restage?
Yes, the bundle can be removed in one piece, and then you can either assemble and disassemble at site, although we normally recommend to go into a repair shop, mainly because you want to have clean and dry conditions when you assemble and disassemble these components.
Great. Sounds like a really flexible design then. Great. Okay, I think Q&A went really well. Thank you for those who submitted questions. Really appreciate that. Rainer, we can go ahead and move on to the next section.
Yeah, I just want to echo Danielle. Thank you very much for the question. They were actually very interesting, and I hope they were also very interesting for all the other people who are attending the webinar. So thank you very much. So we come next to the general principles of gas compression. And this is simply about what does a gas do when I want to compress it, or what do I have to do to a gas to compress it. So it really applies to all types of different compressors. So if I put a gas into a cylinder, and then I have a piston and push that down, then I will increase the pressure of the gas, but I also will increase its temperature and its density. So whenever I compress a gas, that means I increase the pressure, I increase the temperature, and I increase the density. Now the temperature increase only happens if I don't exchange heat with the environment. That is called an adiabatic system. But it's important to understand that I increase the density and I increase the temperature. So what a compressor does, it converts mechanical work into a pressure and temperature rise in the gas. So the compressor uses mechanical energy or work to increase the energy in the gas. And the technical term for that is that I increase the enthalpy of the gas. So this energy increase or this enthalpy increase is often referred to as the actual head of the compressor. So as I had said, this increase in energy in the gas shows as a pressure and temperature increase. Now, the relationship between power and work is that essentially the amount of power that I need to drive my compressor is the mass flow of gas through the compressor times the work that I'm doing. And oh, by the way, there will be losses. For an ideal gas, we have a relatively simple relationship between density, pressure, and temperature, and also relatively simple relationship between work or enthalpy difference and temperature difference. The problem is that the gases that we're compressing at the pressures that we're operating we can't treat them as ideal gases. We have to assume the real gas behavior, and there the relationships become a bit more complicated. Now you see the equations for density looks very much similar, except that I add here this fudge factor of a compressibility factor. The complication comes from the fact that the compressibility factor is in itself a function of pressure and temperature. And also the relationship between temperature and work becomes more complicated. So this compressibility factor is essentially a correction factor to correct the density from ideal gas behavior to real gas behavior. For most of our applications, it's typically less than 1, which basically means that for a given pressure and temperature, the real density is usually a bit higher than the ideal density of the gas. This is a Mollier diagram, and actually one of the neat things about thermodynamics is if I know what my gas is, so if I know the gas composition, and I know 2 things about that gas, then I know everything else. And that's essentially what's displayed in this Mollier diagram that shows pressure, enthalpy on the main axis, and shows lines of constant temperature, constant enthalpy, entropy, and constant specific volume or density in one map. And essentially at very low pressures, any gas behaves as an ideal gas. The only problem is these are usually not the pressures that we have to deal with when we compress our gases. And then you basically see that the compression is defined by a suction pressure and a suction temperature, and a discharge pressure and a discharge temperature. If I then just go straight down and look at the difference in enthalpy between the 2 points, that is the amount of work that I have to put into the gas. An isentropic compression is an ideal compression, and it is actually a very good way of starting the discussion because for many processes, you know the suction and discharge pressure, and you know the suction temperature, but you don't know the discharge temperature. So with the ideal process, with the isentropic compression, I start at my suction conditions, and then I go to my discharge pressure along a line of constant entropy. You can see the work that I do for the isentropic work is lower than the actual work because it's an ideal process. There are a number of other ideal processes used also in gas compression. There is also a polytropic process. The efficiency of a compressor is always defined by comparing the ideal process to the actual process. So here's the isentropic efficiency. Here would be the polytropic efficiency. Now, the problem that I have is these Mollier diagrams work very nicely for pure substances, but we're dealing with gas mixtures. So rather than using the Mollier diagram, I'm using a mathematical formulation that these are relatively lengthy, messy formula, but just picture them as a mathematical representation of that Mollier diagram, but for gas mixtures. And I'm doing exactly the same thing. I'm entering pressures and temperatures, and the equation of state gives me enthalpy, density, and also dew point. There are a number of equations of state that are predominantly used in the industry, and you have to be aware if you use the same pressures and temperatures as an input, you will get slightly different answers. So if you want to be consistent, you really need, first of all, you need to know which equation of state to use, and you need to use it consistently. Now, the differences are not that big, but they are there, and you have to be aware of that. In my example here, just to throw around some names, we use Lee Kessler Blöcker, Redlich Kwong, Benedict Webb Rubin, and Peng Robinson. Now, the gas as being compressible, so the gas flow is measured also in different ways. We use actual flow and standard flow. Now, the actual flow is essentially the amount of the volume of gas that it has at your operating conditions. Let's say at an inlet pressure into the compressor, in this case at 500 pounds and 60 degrees. Standard flow is a flow that assumes the volume of the gas at some specified standard conditions. In this case, 14.7 pounds, so about atmospheric pressure and 60 degrees. So the compressor actually sees the ACFMs, but the standard flow is directly related to things like energy content in the gas. And we are at the point for another set of questions.
Great, thank you for that informative section, Rainer. We're doing great on time. We have about another 5 minutes to take some questions. So one that I think pertains to this content is from Ryanto from North Oil Company. Thank you. Does non-dimensional curve of centrifugal relate to compressor impeller design, Rainer?
We're actually also getting to that in the next section, but yes, the non-dimensional, for example, the head versus flow, non-dimensional head versus flow characteristics depends on the aerodynamic design of the compressor. Okay, so we'll hear a little bit more about that coming up soon. We have a chance to go back. This pertains to the previous section, but if we don't get to your question, we apologize, but I am going to go back to a couple right here. Rainer, can you expand a little bit on what does the labyrinth do, the labyrinth seal for the compressor? Yes, in general, you use labyrinth seals to prevent gas flowing, let's say, in general, backwards through the internals of the compressor. Now, I assume the labyrinth seal that you're referring to is probably the labyrinth seal on the balance piston. And for the balance piston to work, I have to have discharge pressure on one side of the balance piston and suction pressure on the other side, so that I can create a force that counters the axial thrust of the impeller. And to prevent gas from leaking across the balance piston from essentially the high pressure side to the low pressure side, I put these labyrinth seals in there to essentially prevent the gas from moving from the high pressure to the low pressure.
I see. Okay, that makes sense. That kind of addresses a little bit a previous question from our audience about expanding on the balance piston. Does the balance piston size depend on the number of staging? And this is a question from Amir in the audience.
The balance piston depends on a number of things, including the pressure ratio that I make across the machine, which depends on the number of impellers, and also the type of gas that I use, for example. But the question is very valid. You size that balance piston based on the operating conditions that you're designing the compressor for.
Okay, well, that makes sense. Thank you, Rainer, for expanding on that a bit. This is a question from our audience as well. What type of balancing of rotors is done at Solar? High speed or low speed balancing, Rainer?
Well, I really thank you for that question. One of the things that we did in our design in order to make this restaging as easy as possible is we only require low speed balancing for our machines. So the way they are designed, we can do all the necessary balancing to meet the vibration requirements, for example, per API 617, using low-speed balancing.
And what advantage does that create, Rainer, the low-speed balancing capability?
If you have to do high-speed balancing, you need what's called a balancing bunker, and there are not that many around in the world. So you would be very much limited to very few facilities that can actually do this high-speed balancing.
Okay, great. Thanks for that follow-up question. I think the timing is just perfect, Rainer, to move on to our next section of material.
Okay, thank you, Danielle. Okay, now, so far in the last section, I had talked about sort of the general principles on what a gas does when you're trying to compress it. Now we go to the part where I'm trying to explain how a centrifugal compressor does this compression. So we have to talk about essentially how do we transfer the energy from a spinning impeller into the fluid. And we'll talk about how the centrifugal forces help in doing that, but we also talk about, and I mentioned that in an earlier section a little bit, how we can trade pressure and velocity. So let's start with that. If you think about a piece of pipe where I reduce the diameter, so I go from a wider through flow area to a lower through flow area, then if I flow gas through that piece of pipe, then I will see that the velocity at the outlet gets higher, and I will also see that the pressure, the static pressure, actually will get lower. The opposite thing happens when I have a piece of pipe that widens its diameter. So there I reduce the velocity and I increase the pressure. Now, if I go into a typical turbine, then I will see that the flow passages in a turbine exactly go from a larger area to a smaller area. So in a turbine section, I trade pressure to get higher velocities. In a compressor, I do the opposite. I go from a smaller flow area to a larger flow area and trade velocity for a higher pressure. And this is something that's often referred to as Bernoulli's law, about a scientist that I think about 200 years ago or so figured this out. Now, in the impeller, the actual transfer of energy happens as follows. Picture this as a flow channel. So if I have gas flowing in and then flowing out at a different direction, in order to make that gas change its direction, I have to apply a force to it. Now, if I apply that force in a rotating system, then I have a force times the distance, and force times distance is work. So the general principle on all this energy transfer stuff is that I try to force the gas from one direction into another direction. and I do that in a rotating system. So that's happening in the impeller, and then in my diffuser, I convert, and you see that here very nicely in the colors of that graph. You see higher velocities at the inlet, lower velocities and higher pressures at the outlet. So essentially I trade in the diffuser velocity for more pressure. So the compression process is a two-stage process. I enter all the energy into the gas in the rotating part, but what comes out of the rotating part has a higher pressure, but also a higher velocity. And then in the stationary part, I convert a lot of that velocity into more pressure. And actually, a Swiss scientists in the mid-1700s figured that out. And that is today known as Euler's law, after Leonhard Euler. And the important thing of that law is that it creates a relationship between the thermodynamics, the enthalpy changes, and the aerodynamics, which deals with velocities. And basically what he says is the enthalpy change in each stage of my compressor is equal to the change, the change in direction that I force the gas in the circumferential direction times the blade rotating velocity. Which also, by the way, means the faster the compressor runs, the more air is deflected, and so the more work is done. And the other key thing is the only place where work is transferred is in the rotating part. Now, the centrifugal compressors get controlled by either changing speeds, by changing by moving guide vanes, either in the inlet or the diffuser, by throttling and by recycling. Now, in the oil and gas industry, the driver that we use for our compressors allows us to vary the speed. And so in reality, speed control or speed variation is the most efficient way to control the compressor. And you see that on the graph on the right. If I reduce the volumetric flow by changing the speed, then my power demand drops much faster than if I use vanes or throttling. And if I were to recycling, actually, regardless of the flow going through the machine, I always would consume the same power. So you really see here why speed variation is so attractive for controlling centrifugal compressors. So this shows a typical compressor map that for a compressor with that is capable of running at a number of different speeds. And you see here the isentropic work and the actual inlet flow. And you see how by changing the speed, I can modify both the head and the volumetric flow of the machine and maintain good efficiencies in the machine. I'm showing the isentropic head versus inlet flow map. There are obviously a large number of different maps that you can use to display performance. This one shows pressure ratio and flow, actually standard flow. The head versus flow map, though, is the most universal map, and we always use that map, for example, also to evaluate performance of the machine in the field. There is in practically all modern centrifugal compressor a second system to control the flow or the operating point of the machine, and that is the surge control system that allows us, if the flow that's available to the compressor drops below the low flow limit of the machine, we can actually recirculate gas through the control valve back into the inlet. So therefore, and that's basically what recycling is, so therefore we are able to run our station, for example, all the way down to zero flow while still keeping the compressor online. So it's really a method of increasing the overall range of the compressor station. Now, you may ask yourself now, okay, so I have this nice map, but where is the compressor actually operating? What dictates where the compressor operates? And that is really your system. The piping outside of the compressor dictates that. So the system around the compressor dictates the suction and the discharge pressure. And then I can, for example, control the compressor by giving it more power or changing its speed. And then the compressor will react to that system suction and discharge pressure with a certain amount of flow. And that, for example, means if you have multiple machines running from the same header, they will all see the same suction and discharge pressure. So that gets us to the next question and answer session.
All right. Once again, perfect timing, Rainer. Thank you so much. We do have about 5 minutes for some Q&A. Got a question about surge from the audience. Why does the surge effect actually occur? And thank you, Alvaro Reyes, for asking that question in our Q&A chat.
Surge basically occurs when the suction and discharge pressure that the system imposes on the compressor exceeds the capability of the compressor making pressure ratio. So for example, if you run the compressor at constant speed and you increase the discharge pressure, then there comes the point where the compressor simply cannot overcome that discharge pressure anymore. And then the gas that's stored on the discharge side will try to flow backwards through the compressor. That is surge.
I see. So then that's when we'll protect surge from happening with that recycle system? Is that what you were saying?
The recycle system or the surge control system prevents exactly that from happening. So with a well-designed system, the compressor will not surge.
Got it. No, that makes sense. Thank you, Rainer, for expanding on that. A little bit that might still pertain to the recycle system. Question that came through from Peter Davies over during the registration. Thank you for asking in advance. Can you please explain, Rainer, how you reduce the centrifugal compressor throughput without a loss of efficiency?
Yes. That is indeed a very important question when you operate these machines. The method that I've demonstrated is by changing the speed. Because again, if your system maintains suction and discharge pressure, then reducing the speed simply will reduce flow. Now, most system reacts to the lower flow also to a change in suction and discharge pressure. For example, in a pipeline, if you reduce flow, typically your suction pressure starts to come up, your discharge pressure starts to drop. So that will then give you a new operating point. But essentially, you will control the machine or reduce the flow essentially by changing speed or by changing the amount of power that you make available to the compressor, which in turn will lead to a speed reduction if you reduce power and a speed increase if you increase power.
All right, thanks for expanding on that, Rainer. That makes sense and why it's preferred to have our variable speed control. Thanks for going into that. We do have time for one more question. I think this one's interesting, as you know, hydrogen is a big topic in our market at the moment. This one comes from the field. Thank you, Andreas. For Rainer, has solar an understanding of what amounts of 2 to 5 to 10% volume of hydrogen in the natural gas would mean for the compressing process? And are compressor units in operation or built in the last 10 years that are able to handle such amounts between 2 to 10% hydrogen, Rainer? Can you comment on that?
Yeah, there's actually a lot of scare about, in a way, what happens if we add hydrogen into the natural gas stream, and that is being discussed in many countries as one way of accommodating a carbon-free future by using a lot of renewable energy. From a compression standpoint, hydrogen is actually a very benign gas, and the only problem that you have, it's a bit light. So if you add hydrogen to the natural gas stream, you will see that your compressor will have to run faster to maintain, for example, the same pressure ratio. There are also issues with hydrogen, the impact on hydrogen on materials, like hydrogen embrittlement, but these are also pretty well understood. So I would say at this point, if you want to add 5 or 10% into the natural gas stream, you really don't have to modify your compressors, assuming they are reasonably modern. But you may have to restage them at some point in time because you may run into speed limit of the compressor if you want to maintain a certain pressure ratio.
That's a great response. Thank you, Rainer. I think that 5 to 10% threshold in hydrogen and mixing with natural gas is a reality at the moment. So it's good to know that our compressors, fielded compressors, can manage and handle that content today. So thank you. I think perfect timing again to move on to the next section, Rainer.
Okay, thank you. And thanks for all the questions. Okay, now real brief about the sizing of centrifugal compressors. Essentially, I had already mentioned in one of the earlier slides, power is mass flow times work. Now, mass flow translates into actual flow if I know the inlet density, and I know the inlet density if I know what gas I'm compressing and what the inlet pressure and gas temperature is. The actual flow essentially determines the physical compressor size, meaning whether it's physically a big compressor or a small compressor. So that's all determined by the actual flow. Now, the work part. The work is essentially the isentropic work divided by the efficiency, and the more impellers I have and the faster I spin them, I get more work. So that essentially, the amount of work determines the compressor speed, the size of the impellers, and the number of the impellers. And then, of course, the next question is, and that's in particular question when I want to drive that compressor with a gas turbine, does this size match the driver speed? Because the power turbines on a gas turbine, the bigger the gas turbine becomes, the slower the power turbine wants to run, which in general works very well because also the bigger physically the compressor becomes, the slower it wants to run. But that's sort of the general idea how we come up with compressor sizes. Now, Solar has an evaluation tool that's available online that does a lot of these calculations for you. So it allows to enter the process conditions, suction pressure, discharge pressure, suction temperature, the flow rate, and the specific gravity of the gas. And this just shows a sample output. So you enter the process condition, and then the program tells you how much power you're going to consume, how much isentropic or polytropic head that compressor has to make, and what's the actual volume flow rate, and what's the discharge temperature. So that then gives you an idea also how much driver power will I need for my process. But then there's another neat thing you can do with that. And I would like you to remember the isentropic head, about 21,000 feet, and the actual volume flow rate, a little bit about 6,000 ACFM. Because now if you have a isentropic head versus flow map for this compressor, even though it was created for somewhat different operating conditions, then you can use your 21,000 feet of head and your 6,100 ACMF of flow, and you know that this particular compressor will operate at this operating point at, in this case, at about 8,500 RPM and an efficiency well in excess of 86%. So that's why I said these maps are very universal, because you can use them even if your operating conditions change a bit. And then, of course, when we size these compressors, in general in the oil and gas industry, there is no one design point. You always have to size for different operating conditions. So you have to think a bit about how you best place your compressor map relative to the operating conditions. And so if I have these 4 operating conditions, you see that I can size a compressor that I can run all these 4 points without recycling. But that means that my point number 4 is probably not all that efficient. Now, if this is my most important point, then I would use a map that that runs my point 4 efficiently, and I would recycle my point number 1. So these are design choices that when we size compressors, when we pick impellers, we take into consideration to match the machine to the operating conditions. Now, you may always wonder, so how does the compressor actually adapt to changes in process conditions? So I've demonstrated that here. So let's say this is our compressor map. This is our design point. Now, all of a sudden, my gas gets heavier. Happens a lot. So if my process control is set to maintain the original discharge pressure or the original pressure ratio, then all the compressor does, it will slow down, and it will slow down because I reduce the driver input from the driver. If the suction temperature is rising, again, same thing, the compressor will speed up, the driver will provide more power. If the suction pressure changes, in this case it's rising, then again, the compressor will maintain discharge pressure simply by slowing down, and that is accommodated by changing the power from the driver. So you see that actually centrifugal compressors are extremely flexible and extremely easy, adaptable to changing operating conditions. Again, these are examples for variable speed compressors. Now, coming back to the hydrogen question, actually, what you see here is a compressor map where this would be my operating point for natural gas. And you see how these operating points are moving. And eventually, I will hit the maximum speed of the compressor. Now, if I want to go higher in hydrogen content, I would have to restage the compressor so that it simply makes more head. So I, for example, would add an impeller to that compressor. So we're at the point where you can ask questions again.
Great, thanks, Rainer. Great timing once more. Couple questions with the similar theme in our questions from the audience. Why in compressor performance curves does Solar use the isentropic head versus polytropic?
Very good question. I mean, the easy answer is we can make these curves both for isentropic and for polytropic head. So it's really very much a user preference. I would like to point out, though, that if you integrate a compressor in a compression process, then from a process design standpoint, you typically know what your suction and your discharge, what your suction pressure and temperature is, and you know what discharge pressure you want. That fully defines the isentropic head. It does not define fully the polytropic head. But again, from a map generation standpoint, we can do either one, and they both have about the same value when you want to compare different operating conditions.
Okay, that makes sense, Rainer. That's good that we have the flexibility based on, you know, an operator's familiarity with either isentropic or polytropic. So thank you for answering that. Question regarding the surge line and how it moves when the gas composition changes. How does the surge control system know when the gas composition changes and how to adjust?
That is actually a really good question, and one of the things we probably will do is a complete webinar on surge control. The easy answer, the answer is that the that you can set up your surge control system, that you define your surge line in a coordinate system that is not depending on the gas composition. And that sounds like a bit of a weird answer, but the key thing is that with a modern surge control system, you do not need to know the precise gas composition when you operate the machine.
That's good, and especially as the composition may change.
Yes.
It's good to inherently know that the system is designed for that, those shifts. A little bit more on surge, actually, a question from the audience. Could you elaborate on typical indicators of surge or the possible consequences as a teaser to our next webinar?
There are a number of things that might be indicators that you're reaching the surge line. Conceptually, a surge control system simply looks where you're on the map, and then if your operating point moves closer to the surge line on the map, it takes corrective action by opening the recycle valve. Some machines show increased vibrations when you get near surge. Some machines will show, if you have a flow measurement right in front of the compressor, you may see that your flow measurement starts to get a bit wiggly and you get a lot of noise. If you look at the operational map, you will see that once you approach surge, your head versus flow characteristic will flatten out. And the reason why I'm a bit vague is because the signs of approaching surge are different from compressor to compressor.
Oh, that makes sense, Rainer. Those are all good characterizations of when you're approaching that surge point. So thank you for clarifying for the audience. This is an interesting one. What is the stone wall?
The stone wall, another expression for that may be overload or a choke, is essentially the high flow, the high operation of the compressor at very high flows. So if you just picture, let's say if I have a compressor on a test stand and I run it deliberately at constant speed, and then I have a throttle on the discharge side of the machine. So if I close the throttle, I move the machine on that constant speed line towards surge. If I open that throttle wide, then what I will see is the amount of head that I make will be reduced, but the flow will go up. And on some machines, you will get to the point where even if I open that discharge throttle wider and wider, the pressure will drop, but the flow will no longer increase. That is sort of what the classical choke or stonewall situation is. That also comes with typically a significant reduction in efficiency. And then it depends on the design of the compressor, whether the manufacturer puts in limitations on how far into the high flow region you can go. We typically don't limit that with our machines though. But the short answer, choke, stonewall, overload, it's all refers to operating conditions at very high flow and very low head.
Okay. I see. That was a good description of it, Rainer. I didn't exactly know what that was either. When you're at that point, approximately, like you can start evaluating the compressor design and potentially restage or get it closer to the more optimum design?
Well, it really depends. There are a lot of upset conditions where you, for a short period of time, run in stonewall. Typical example is if you have a brand new pipeline and you start filling gas into your pipeline, then for a while you will operate your compressor at very low pressure ratio. And if you want to make that filling as fast as possible, you want to maximize the flow. So you're going to run the machine in stonewall.
I see. Thanks. So more of an upset condition occurrence. That makes sense. Okay, Rainer, we're ready to move on to the next section of content. Thank you so much.
Okay. So I want to talk a bit about configurations on these machines, especially on the packaging side and drivers and stuff like that. So we so far mostly talked about a single compressor body. But what if I want to make more pressure ratio than what I can get out of single body? Or what if I want to have side streams? Or what if I want to have the capability to cool the gas during the compression process? In all these instances, you have a number of options. You either can have two individual compressor bodies driven by the same driver. You can have a casing with two sections. And these two section casings, you can either have them with all impellers pointing in the same direction. That's typically referred to as straight through compressor or inline compressor. Or you can have the first sections, the impellers pointing this way, and the second sections, the impellers pointing this way. That's usually referred to as a back-to-back configuration. And the considerations that really make that decision on which configuration you want to go depends a lot on what you want to do with the compressor, how much operating range you need, what operating flexibility you need, and are there any restaging plans? How do you balance thrust loads in transient and off-design conditions? How do you deal with interstage leakage? And there's obviously always the question, okay, what's the least expensive version, and how do I deal with restaging? I want to focus a little bit on the thrust load because there's a lot of opinions out there that I would like to address. So if I compare an inline compressor, and you see here that the impellers in the first section and in the second section all point in the same direction. So the flow through the impeller is from here to here, whereas on a back-to-back machine, the flow in the first section of the impellers is from here to here. In the second section, it is essentially just the opposite direction. And so the theory is that this design doesn't need a balance piston because the axial forces of the impellers are balanced. And that is true for the design point, but it's not true for the off-design points. So what you see is when you operate a compressor from near surge all the way into choke, the axial thrust will change. And actually what we will find out is that in inline design, the change in thrust load between an operating point at near surge and an operating point in choke is actually less than with a back-to-back machine. So that means a couple of things. One of them is that yes, you will most likely still need a balance piston for a back-to-back machine, and you may have more limitations on how the operating conditions between the first section and the second sections are going to change. The other area is really about process flexibility. I just want to show an example here for a field compression. And what's happening is typically in these gas fields, over the lifetime of the field, you will see a reduction in flow and a reduction in suction pressure once you decline the field. So you see here, this gray area is what the compressors were originally designed for. The red area was how they were operating at the later stage of the field. And one of the ways you can accommodate that is that you build two-body tandems where you are able to add a compressor body in the later stage of life when you need a lot of pressure ratio, and you accommodate the changes in flow by restaging these machines in several steps. Now, the neat thing about the modular rotor is that in these restaging procedures, you don't necessarily have to exchange entire rotors, you may be able to just get away with just replacing 1 or 2 impellers, or also reusing these impellers at later stages of the project. So that gives you a lot of extra flexibility. Another area where operating range becomes very much of an issue is if you have gas storage applications. So where you essentially fill a storage capacity, and it could be an old gas field or could be a salt dome. So you essentially push gas from pipeline pressure into your cavity, which basically means while you push in the gas, your cavity pressure increases, and then you can essentially empty that cavity. That essentially gets you to operating conditions where initially you have a low pressure ratio, like here, and later, like here, you have a high pressure ratio. And there you can do some neat things by having 2 individual compressors driven by the same driver that you can initially run in parallel and then later run in series to give you a very nice operational flexibility. So these are just some examples on how configurations can be used to better adapt compressors to given operating conditions. And then this is how these trains may look like. So we have here a gas turbine driving a single compressor body. This happens to be for a pipeline application. You see here a 3-body tandem. So you see 3 centrifugal compressors driven by the same driver, and you put a gearbox between the first and the second body, which allows you to then run the higher pressure bodies at a higher speed because these are smaller compressors. Or you have 3 bodies with a gearbox between the driver and the first compressor. Or, as I had mentioned, you can also combine 2 sections of compression into a single casing, like in the lower right pictures. And again, it depends a lot on the application, what's the preferred solution. I had mentioned that we often see gearboxes in compressor trains. Again, here it's between the driver and the first compressor. Here it's between the first compressor and the second compressor. And that allows you, for example, to better adapt your compressors to the driver speed, or to better adapt the high pressure compressors in your compressor train to run them at a higher speed than your lower pressure compressor. So there's a lot of flexibility to be gained by using gearboxes.
Hey, Rainer, I just want to jump in real quick. If you want to use your laser pointer to point anything out, there you go. Okay. Oh, okay. I wasn't seeing it on the screen. Thank you.
Thanks. So yeah, you see the gearboxes here between the driver and the first compressor. Here the gearbox would be between the low pressure compressor and the high pressure compressors in that application. As far as the drivers goes, and I hinted a few times on this, centrifugal compressors in the oil and gas upstream and midstream industry are very frequently driven by industrial gas turbines. These are 2-shaft gas turbines, so I have actually a driver that allows me to vary the output speed over a very wide range, and so that makes it very elegant with the speed control concept of these centrifugal compressors. We also use electric motor drives with variable frequency drive that also gives us the capability to vary the compressor speed. So you see here the electric motor, a gearbox, the compressor, or we can use variable speed gearboxes. So you would have the motor here, you would have a gearbox that for constant input speed allows us a variable output speed going into the compressor. That really gets us to the end of our webinar. So I hope I've given some insight on the general principles of gas compression and how these centrifugal compressors work. I talked a little bit about how they are sized in general. and what kind of configurations you can expect depending on the applications that you're using. I really want to emphasize centrifugal compressors are not very complicated. They have very few moving parts, but they are probably a bit more difficult to understand how they are working compared to other types of compression. So with that, I think we still have some time for questions.
That's right, Rainer, we do. And thank you for everybody who's been sending in questions. We're taking a look at them. We also have time to put up our first poll for people that participated in the beginning. You'll recall to go to the same link in the chat window. You should see a new one active. So when we get a chance, we'll put the results up for that here. While we're waiting for the poll, this question came in from the field. Or from the audience, excuse me. Does solar have criteria for how long a compressor could cross the surge line in one surge cycle?
We try to keep our compressors from surging. I do know that when you go in the field, you see a lot of compressors, centrifugal compressors that will surge at some point in time of their life, and I have not yet seen a compressor that was damaged by that. However, I don't think anybody has a good guideline that says, okay, you're going to have a problem after 50 surges or after 100 surges or after 200 surges, because it depends a lot on the circumstances. So what we try to do is we try to design our systems and help our customers to size surge control systems that prevent compressors from surging.
Great, Rainer, thank you. And thanks for that question from the audience. I hope that clarified that there's no real industry standard on how long or how many times, but that we try to optimize the system for you together. So thank you for those who are participating in this poll right now. The question up is, what topic are you most interested in for the next in our compressor series of webinars? I've definitely noticed a number of questions on surge and surge control in the Q&A. Looks like that one's coming out ahead, but this is good to see that there's equal interest also in control and then optimization of actual centrifugal compressor trains. Let's leave this one up, Will, for a little bit longer while people continue to respond to it. And I'll ask another question, a little bit about compressor trains, Rainer. Earlier on in this section, you showed a number of different configurations. What configuration allows the highest pressure ratio, and what is that maximum pressure ratio you can reach with that given train?
If you put 3 compressors in series, that is probably the configuration, or actually ranging compressors in series in general gives you the highest possible pressure ratio. Now, if you compress natural gas, then you can get with a compressor train, meaning a train that is with multiple compressors that are all driven by the same driver, you can get to about a pressure ratio of 30. The requirement is also that you do intercooling, because if you don't, the temperatures go higher than what you normally want from a process standpoint, and also without intercooling you would consume far more power. But you can make a train that does a pressure ratio of 30 on natural gas. And the reason why I'm emphasizing natural gas is because it depends a lot on the gas that you're compressing. These 3 compressors that I mentioned, and all stacked with the necessary impellers, would get a significantly lower pressure ratio if you were to compress hydrogen, for example. I
see. Thanks for clarifying that 3-body configuration, high pressure ratio. When you touched on intercooling, intercooling of the gas in that situation, any other times you need to intercool, or is that mostly the intent of intercooling?
Well, the intent of intercooling is twofold. One is you try to keep the temperature of your gas typically below about 350 degrees Fahrenheit or so. I mean, this is not a hard and fast number, but that's typically used in the industry as the guideline. The other thing is that if you compress gas, and you can intercool the gas, the amount of power that you consume for the same purpose will go down significantly on high pressure ratio applications if you cool the gas.
I see. Great. Thanks for expanding on that a bit, Rainer. This is a question that we received from the audience as well. Can you start in a pressurized hold condition or compressors?
Yes. That is actually one of the neat things about driving centrifugal compressors with especially gas turbines, because a gas turbine gives you a lot of startup torque, and so therefore it's not a problem to start a compressor from a pressurized hold condition. You get similar advantages with variable frequency electric drives. If you have a centrifugal compressor with a constant speed motor, then the starting of the equipment could become a significant challenge, because then it depends on how strong your electric power supply is. And for constant speed motor-driven compressors, you may end up having to reduce the pressure that the compressor sees during startup.
I see. Well, that's good. So yet another advantage of a variable speed controlled compressor. Good. Thank you for addressing that. Here's another question from the audience. What is the experience at Solar Turbines for conducting string tests with gas turbine driven compressor with a generator? Have any testing been done at Solar Turbines, and give some insights on testing?
Okay. I sense there are two questions. Yes, we do string tests, and we've done string tests with gas turbine-driven centrifugal compressors. Our test facility allows us to do that, and we can do string tests where we actually run the compressors in a closed loop, so we can essentially fully load the driver. The combination of electric motors and gas turbines on the same train, I know is very common for large LNG applications, but there it's very much driven from the fact that if you have a single shaft gas turbine, not a two shaft gas turbine, then starting becomes very complicated. So you often use electric motors, large electric motors, as helper drivers to accommodate the starting of the train. You don't need that for two shaft gas turbines, really. We've worked on a number of projects where the discussion was about combining electric motors and compressors, electric motors and gas turbines as the drivers for compressors because of either the availability of low-cost electricity or the temporary availability of electricity and things like that. We haven't built one yet, mainly because in all these cases where we worked on it and designed for it, the end user simply could not make the economics work. But it is definitely a possibility to do this.
That's great, Rainer. Thanks for expanding on that. So our closed loop test facility in San Diego, California, that can test any compressor body size in combination with a solar gas turbine?
Yeah, I mean, okay, you're again asking two questions. The closed loop test facility that we have uses a facility driver. And that is used for ASME PTC10 type 1 and type 2 tests, for example, and also a lot of our internal testing. In a string test situation, you would use the contract driver to drive the contract compressors. Now, sort of factoid on the side, we have that capability. We see hardly ever customers who want to use that capability, and that comes to some extent that we use a lot of pre-engineered and pre-tested design. So if you buy a train, we probably have built something very similar already and have that in operation. So the testing requirements are in general not limited by our facility capabilities, but really by what's useful for a given project.
Great. Thanks for clarifying that, Rainer, and asking my combo questions that I am able to craft. I think this is a perfect time. Thanks for responding to this poll question, everybody, for us to put up our final poll question. So we definitely want your feedback on how you like the format of this webinar, specifically the timing of the webinar. Are you comfortable? Do you like this 90-minute format of today, or would you prefer 60 minutes? So I definitely see some, looks like 90 minutes is coming out ahead at the moment. We'll leave this up for a little bit and see if we gain some consensus. Okay, Rainer, we have a few more minutes. We'll take some more questions from the audience. What are the consequences of running a centrifugal compressor beyond its lifetime?
Well, the first statement is that there is no lifetime limit as such. Now, obviously, if you damage something within the compressor because, I don't know, because, for example, you all of a sudden have a lot of sand in your gas, then that is lifetime limiting, but there's no conceptual limit for a centrifugal compressor. Now, there are often practical limits because the development or a compressor that you may have bought in the 1960s, and there's still quite a few of them around, is performance-wise and maintenance-wise clearly inferior to a machine that we would be building today. So the limit is more often than not just a technology limit where it's simply more economical to put a new machine in. The other thing is, of course, also that that in many instances the installations that use a centrifugal compressor also may have a limited lifetime. If you have a gas plant, for example, you may after 30 years or so make some major modifications, and that may include upgrading the compressors. But conceptually, there is no lifetime limit for a centrifugal compressor.
All right, thank you, Rainer. And thank you for everybody that's responded to this poll. It seems like the 90-minute format is preferred, and I thank you, Rainer. We got through a lot of content. I'm going to go ahead and share my screen here. One moment. Okay, so we're doing great on time. We just have a couple minutes left. Rainer, I want to share with you one, not really a question, but a request from the audience. If you could please write a book on compressors, like you did most recently with the gas turbine.
Actually, the good news is I do.
Oh,
so with a little luck, we'll have one sometime next year.
Oh, that's fantastic news. I think everybody on the line will appreciate that. I think we have time for maybe one more question. We have 2 minutes left. Rainer, is the solar compressor rotor considered flexible or rigid, and since it's only low speed balanced?
It operates above the first critical and below the third critical. So in that sense, it bends. But obviously, and I'm a bit hesitant to be more clear than that, because essentially where in that range you operate depends also on things like bearing stiffness.
Okay. Well, thanks for being able to approximate your answer there. We do want to thank everybody for joining us today, and Rainer for all of your insightful information shared. A shout out for everybody on the line here. Please follow us on social media. We have some great content that comes through in our Facebook feeds, Instagram, LinkedIn, Twitter, and new YouTube videos that are released quite frequently, and new content's coming out all the time. So follow us so you get those notifications. And again, this will be available on our website, www.solarturbines.com. Under webinars, you can navigate through the menu bar. And with that, I want to thank everybody for taking the time with us today, asking insightful questions. Rainer, for all of your content shared and answers provided. We hope to see you next time, everyone, and look out and keep an eye out for when our next webinar on compressors is. So thank you very much for your time.